In this next set of slides, we'll be going through sequencing in a integrated circuit and how to design sequencing elements, latches and flops. Then we'll go through the timing of sequentials and sequencing, what we call max delays and min delays, what they mean, how you calculate them. Go through a little bit on clock skew, time borrowing, and two-phase clocking. So those will be in the upcoming presentation. In an integrated circuit, we have combinational logic, and that basically is outputs depend on the current value of the inputs. We've talked previously about sequential logic, where the output depends on both the current value and previous inputs. So basically it requires separating previous, current, and future values, and so we get what we call state out of it. So something that will stay stable even if some of the inputs change. For example, we might have a pipeline similar to what's shown below, where we have a sequential element that has a clock, and we only switch the output based on when the clock either is high or when the clock switches from low to high, depending on whether we're talking about a flop or a latch, which we've discussed in previous lectures. And the output of that sequential will change, go through some combinational logic, and it might take some time to get through that combinational logic, but eventually it should provide a stable value as long as all the inputs to the combinational logic change only once. Eventually the output of that combinational logic will provide a stable value after a certain amount of time. Once that's stable, we can then have our clock switch again, capture new values in the second sequential, and send that through a set of combinational logic. And so you can see every time the clock changes value, we could have logic going through the following output combinational logic till it becomes stable, and then we can have this clock capture it again, and everything kind of goes in a pipeline. There's also something called a finite state machine, where you can have the output of a set of logic feed back to the combinational logic that feeds back to its input, and you wait until it's stable, then you clock it again, you go back through the combinational logic and until you become stable again, then you clock it again, etc. Every time you clock it, based on its own output plus potentially other inputs that might be coming in from other places, you can change the state of the value that you're at. So doing this is called sequencing. Continuing our discussion on sequencing, so if tokens move through our pipeline at constant speed, we might not actually need sequencing elements, might not be necessary. Just as an example, if you have a fiber optic cable, you can send light pulses as your tokens down the cable, and since light travels at a relatively constant speed through fiber optic cables, you can know when you could send a next pulse as long as you send it at constant intervals and the receiver knows what that interval is. You don't necessarily need to have hardware to separate your pulses. You can just send them down and the receiver can receive them, and your pulses aren't going to catch each other and interfere with each other. Now there is a certain minimum amount of time between pulses set by dispersion, where if you know even fiber optic cables, depending on the parameters and the material itself, can have some variation in it. So dispersion could set what minimum time you need between your pulses, and this is termed wave pipelining. Now in most circuits you can actually have quite a bit of time delta, as we saw previously, between our propagation delay and contamination delay, and so the dispersion can be quite high in most circuits. So trying to add extra delay to your fast tokens so they don't catch your slow ones can be very difficult and tricky to do. So most of the time we will rely on the sequencing that we do in order to make sure that we keep everything in good sequential order. So we get something that is known as sequencing overhead. We'll use flip-flops in our circuit in effect to wind up delaying the combinational logic that's fast. It needs to wait for the next flip-flop to sample it in order to continue on doing its function. And so any combinational logic path that's really fast is sitting there waiting at the input to a sequential or flip-flop element, and any ones that move slower will wind up changing just as they get to the flip-flop that is trying to sample it. They get there just before it switches, so the slow ones don't really wait, but the fast ones need to wait. So inevitably this is going to add some delay though to even the slow tokens, because you need to make sure that even the slow token gets there just before the element switches, and so you know, you can't get it there at exactly the same time every single time such that you don't get any delay. And the flip-flop element itself takes some amount of time from its input switching to the output to switch, so there is overhead and extra delay through the sequential elements. So adding these sequencing elements does make the circuit slower than just having pure logic delay, and this is called sequencing overhead. Some people will call this clocking overhead, but you're going to have this type of overhead in asynchronous circuits too. Asynchronous circuits are ones that don't use a clock. They let things go through without clocking. But if we want to maintain the sequence of events in the right order, it's an inevitable side effect that we have to have this sequencing overhead. Now, in a previous week we went through the sequencing elements, the basics of it. We'll go through a little bit more detail this week, but let's start out with a quick refresher of the basics. We have two basic types of sequential elements. A latch is level sensitive. In other words, it's sensitive to the level of the clock. If the clock is high, a transparent D latch, the standard one, allows a D signal to go out to the Q output as long as clock is high. A different type of sequencing element is the flip-flop. This is edge triggered based on the edge of the clock. So a master-slave flip-flop is typically what we're talking about. There are other types of flops, D flip-flop, D register, but right now I'll talk about the master-slave flip-flop. And this allows a signal, input data signal D, to go get captured and go out to Q when the edge of the clock switches between 0 and 1. So as the clock switches from 0 to 1, at that instant in time it captures the value of D and sends it out to Q. So looking at the timing diagram for these two types of designs, the latch design is either transparent when clock is high or opaque when clock is low, and doesn't have a concept of edge triggering, whereas the flip-flop is edge triggered. It captures a value only when clock goes from low to high, and otherwise it's always opaque and it's never completely transparent. So let's look at the timing diagrams here, and we can see if we had a clock switching like is shown and a data switching like is shown, when the clock goes from low to high, the latch, when clock goes high, the latch decides, okay, I need to follow the value of D. I'm transparent and I'm open, and I allow the D value to come through. So the latch value goes low to match D. The flop on clock switching from low to high also switches, it captures the value of D and says, oh, D is a 0, so I'm going to go from high to low and capture a 0 value. Now, as we follow the waveforms along, D switches back from low to high. The latch will follow that D value going from low to high, and also follow it going from high to low, because clock is still high. As long as clock is high, the output Q of the latch will follow the value of D, and so it will switch. On the other hand, the flop stays low the entire time because it only captures the value at the instant when clock went from low to high. So it ignores the value of D all other times. So now if we continue following the waveforms along, clock eventually goes low, and when it goes low, the value of D was low at that time. The value of Q was low because it was following D. And then a little bit farther on, the data value goes high when clock is still low. At the time that clock is low, the latch is ignoring the value of D, so it stays low, and it continues to stay low until eventually the clock goes high again, and then when clock goes high, the latch becomes transparent and it follows the value of D at that point, and the flop samples the value of D at that instant, which is high, so the flop goes back high. So that explains the functionality of the latch versus the flop, and we'll go into more details on different types of latches and flops that we can use in the next few foils. The most basic type of latch design is to use a single pass transistor as a latch. And this was used way back 40 years ago or so in the 1970s. The pros of this is it's tiny. You're just using a single transistor in order to produce a latch. And it also has pretty low clock load because the clock only needs to go to the gate of a single transistor. The way that this is attempting to be used, though, is you use the clock going into the gate of the transistor to allow the D value to be driven out to the Q value, but when the clock goes low and that transistor turns off, you're basically not driving the output Q to any value. You're relying on the capacitance, the inherent capacitance on the node Q to just hold that value. This of course has several cons. One con is you're only using an NMOS transistor to try and drive both 0 and 1. So if you're trying to drive a 1, you get a threshold voltage drop at the output, and so you don't get a full VDD value out, which is a big con. Second is it's non-restoring. By that means you don't get an active drive, you get a passive. It's just passing the D value through. So if the D value was even less than, let's say, VDD minus VT, at most Q can only get up to whatever the value of D was, and so you don't get a full restoring to a 1 or a 0 level. Or if D wasn't pulled down all the way to ground, Q wouldn't get pulled down all the way to ground. Next one is you can get back driving. So when your pass gate first opens up, if the D value was a 0 and Q value was previously a 1 from the last time you opened the clock, the Q will start trying to drive current back into D, and it could actually interfere with the value that you were trying to drive in if you didn't have a good driver driving into the D value. It's also sensitive to output noise sensitivity. So when, for example, when you turn this latch off, so the clock turns off and turns that transistor off, if there's some sort of noise source that puts some noise on the Q, you're no longer driving it at all. It's completely, you know, undriven. And so any noise source on Q will just directly go on Q. It won't get overridden and pull the value back to either a 1 or a 0 like you would want. It's dynamic in that, you know, basically the values can change when you're not driving it, and you have a diffusion as your input, and so instead of going just to a gate, going to a diffusion, you get more potential current, parasitic current going through that gate, which can cause problems for the amount of load on your previous stage. So going to a gate of a transistor, you have no current draw. Going to the drain, you can get some current draw even when you turn that transistor off. A slightly more complex latch design is to use a transmission gate. So instead of using just a single transistor, you use both an NMOS and a PMOS transistor. An additional bonus to this compared to the previous one is you don't get any VT drop. You still have all the cons of the previous design that were mentioned, and one additional con to this design compared to the previous one that we just talked about is it also requires an inverted clock. So you need to invert your clock, and you're going to have more clock load on this than the previous single transistor pass design. But at least you don't get the VT drop through this type of latch design. Again, you still have all the other cons that were listed from the previous foil. Continuing to add on to our latch design, we can, instead of just using a pass gate, we can do a pass gate followed by an inverting buffer. We get a few additional pros and cons from this design. So one pro is it actually is a restoring design. So if we have a value come into the data input that isn't quite a 0 or 1, our output will get restored, inverted, but restored to a full 0 or 1, and we don't get any backdriving. So one con that is removed is the backdriving doesn't happen because we have that buffer in there. And this can, depending on whether you have the inverter before or after the pass gate, this can either fix your output noise sensitivity. So if you have the inverter after the pass gate, you fix the output noise sensitivity since you're always driving the output Q bar value with a strong value. Or if you put the inverter before the pass gate, it will solve the diffusion at the input, since now your D gate is, or your driver D value, previous driver is now driving into the gate of an inverter instead of driving into the diffusion of a pass gate. Now, the one additional con to this design is your output is an inverted value. Instead of being a pure buffer, you now have an inverting latch design. In some cases, this may not be a concern to you. You might actually be able to use this inverted value. So it's not always a con to you, but it could be a con depending on your implementation. Adding yet more to this latch design that we've been working up we can add a feedback element into, instead of just having an output inverter, we add feedback to the internal X node. So this has a benefit that it's now a static value. So previously we said it was dynamic, where we're relying on a charge being held dynamically. And if you take too long between, when you actually try to store a value in a latch and you wait too long and expect that value to just be held there, eventually kind of parasitic current and noise and other things are going to cause that X value to degrade over time. So holding state dynamically can be dangerous if you're trying to do it for too long. You can only do it for a short period of time. This, because there's active feedback with that tri-state feedback, gives a static value that will stay there over time, and you can wait pretty much as long as you want to, as long as you have voltage and power being supplied to your circuit, and it will keep that same value. Again though, this actually adds a little bit more to even your backdriving risk. So when you open the pass gate at the input to this latch, the value that's in X is going to try and drive back and override the value of D. And this is made worse by the fact that we now have this feedback device that's actively driving X. And so we need to make sure that whatever is driving the D node, the input data node, is stronger definitely than the feedback element inside the latch. And basically here, static latches are, for the most part, now essential. This type of design, we can't use the dynamic latches in modern processes because of the fact that we have so much leakage. The leakage of our transistors has gone up by so many orders of magnitude from like the 1970s to today that you can't rely on dynamic latches that don't have this type of tri-state feedback or some sort of feedback in modern process technologies. Continuing on with our latch design, one additional element that we can add to it compared to the previous foil is to put an additional inverting buffer at the input before we go into the pass gate. This buffered input latch fixes our diffusion input. So previously our data was going directly into a diffusion, which is more problematic than just being received by gates, and so this fixes that. In addition, this is non-inverting, and so if you want to have your output follow your input and basically just be a buffer and not change the value of the value of the information that you're capturing, this is better in that sense. And an additional thing that's not listed on this foil is you can see there's no backwriting issue anymore. Because when the latch opens, you have that inverter already built into this design, and you make sure that you will size that first input inverter to be large enough so that it will always be able to overcome that feedback tri-state. And so you have control of that in this cell itself, and make sure that you have everything sized correctly so that you won't backwrite and overwrite the value that you're trying to write in. Continuing on with yet another variation of the latch design that we've been working on, we can add an additional buffered output. The benefit that this buffered output has is if you have any noise on your output Q, so Q is going out and driving maybe multiple other receivers, if those receivers try to backdrive any noise onto your latch, the buffer will not allow anything to go back and interfere with the state node X. If you go back and look at the previous foil, you can see that when we had our inverter that drives the tri-state, when we took our output at that inverter, between the inverter output and the tri-state input, if you happen to get any, since that's driving out to potentially multiple receivers, if you had any noise on that, that could potentially go through the tri-state and interfere with your state node. So this does not have that problem in its design. For this reason, this standard cell is widely used in the industry in standard cells. For the main reason, it's very robust. You can use it pretty much in any sort of circumstance you want. For whatever driver might be driving into it, it's tolerant of lots of different drive strengths. For whatever thing you might want to drive out of it, it's tolerant to lots of noise, and so it's fairly robust to use in any circumstance. The downsides are, since it has more transistors than all of the other ones that we looked at, it's a larger latch than other ones. It's a little bit slower. It has 2 inversions along with the pass gate. Some of the other latch designs we looked at had only a single inverter, so they could be almost twice as fast. And it does have more clock loading because you have both a PMOS and an NMOS in your pass gate, and you need to create a clock and a clock bar version of your clock in order to make sure that you clock both sides of the pass gate. So, it is a good design, but there could be reasons why you might want to use one of the other designs that we talked about earlier. One final latch design we'll talk about is kind of a combination of the last one that we just looked at, and then also going back and pulling the inverted latch design that we had talked about previously instead of a non-inverted latch. So it removes the inverter at the input to the latch, so we don't have any buffer at the beginning, but it adds a external separate output inverter rather than using the feedback inverter as our output signal. So the benefit of this latch is it's a little bit smaller than the one that we just talked about. It removes one inverter, so that helps us with area. And it's going to be faster since it only has to go through a single pass gate and inversion, so it can be not quite twice as fast, or half as slow, half as fast. It'll be faster than the previous design because you go through less propagation delay, and the downside is you no longer have a buffer on your input, and so that could cause problems with depending on the drive strength. If you don't know what is driving into this latch, it could cause problems. But as long as you know where you're using it and what is driving into it, you could be okay with this type of design and get a faster, smaller device out. Now let's go on to flip-flop designs. We've covered this in a previous set of lectures, but let's go through this, the basics again first, and we'll go into more details of types of flip-flops as well. So the basic flip-flop design is built as a pair of back-to-back latches. So as we can see here, this is a starting, you could say this is a buffered latch with inverter, pass gate inverter, followed by an unbuffered latch where it's just pass gate inverter for the top design there. And the bottom design you could view as inverter, pass gate inverter, followed by a pass gate inverter and then have an additional inverter if you need a lat or a flop that is has both Q and Q bar output. So depending on, the top one is a D input and an inverting Q bar output, and the bottom one is a D input with Q and Q bar on the output. The key thing to remember is a flip-flop has a master latch followed by a slave latch, and those are inverted in how they respond to the clock. So this is being done if you look at the clock and clock bar that are going to the pass gates. The front pass gate has the PMOS going to clock and the NMOS going to clock bar. The second pass gate has the PMOS on the bottom going to clock bar and the NMOS going to clock. What this causes is when clock goes high, the second pass gate that is the slave winds up opening up because clock goes high, the NMOS turns on, clock bar goes low, the PMOS turns on, and the master will turn off and capture the value X and hold it during the entire time that the clock is high. When the clock goes low, the slave closes and continues to hold the value of X, and the master opens. It allows a new value of X to come in, but since the slave isn't looking anymore, the slave holds the old value of X. So again, a flip-flop will only change value when the clock goes from low to high. The master will push its value to the slave, and then that value will be held until the next time the clock goes from low to high. Next, let's talk about some additional features that you can add to both latches and flops. The first of those is adding an enable. This is a signal that tells you, or tells the circuit, to either enable you to capture a new value. So what it's going to do is, if the enable is 0, you're going to ignore the clock in effect. So whether the clock switches or not, if enable is 0, you say just keep the value that you currently have. So there's a couple different ways that you can do this. You can either do this with kind of a mux design, where you add a mux, 2-to-1 mux, for example, at the input to either the flop or the latch. So if you look below, we have a symbol on the left-hand side for either a latch or a flop in the first column. Second column, we have a multiplexer design. So we add a 2-to-1 mux, and we have an enable, which either says if enable is 1, we choose a value of D, so a new value of D coming in that goes into the latch. And so if the clock switches, we choose that new value of D if enable is 1. But if enable is 0, we have the value coming out of the latch or flop going into the 0 input. And if enable is 0, the clock can switch, but we're going to choose the output value from the flop going back to its input, and so it will stay the same value even as the clock is toggling. So the mux can basically be used as one design. Second type of design we can do is we can take an AND gate and have the clock go into an AND gate along with enable as the other input to the AND gate. So if the enable is 0, the output of the AND gate will always stay 0 and will never switch. So the latch will always stay closed, keep the same value even as clock is toggling. For the flop, the input to the flop will always stay low, so you'll never see a transition from 0 to 1, and the flop will keep the same value. And only if enable is 1 will the output of the AND gate will just follow the value of clock, and then the latch and flop will behave as normal. So The one problem with using the MUX type design is the MUX will actually increase the amount of time it takes you to get a new value of data through to Q, because now the value of data needs to go through the MUX and then through the latch or flop, and so you get a little bit more delay from D to Q in your design. So you might say, if I care about the delay from D to Q the most, then I want to add clock gating instead. But clock gating will add to your clock skew, which can be a little bit of a problem, and it will also increase your setup time, and we'll get into what setup time means in the future foils. Another feature that is added commonly to both latches and flops is a reset function. So a lot of times you want to say, okay, we're either capturing data, or there could be a global reset comes through the system and says, I just want to reset everything and start from scratch. So implementing a reset function, there's a couple different ways we can do it. Down below we have shown a latch and a flop, and how you might implement reset in a latch versus a flop, and the two different types of reset. So there's synchronous reset, and synchronous reset, what that means is we don't, if a reset comes along, we don't just automatically overwrite the value of the latch or flop to the reset value. We still wait for the next clock to come along and sample that result. And so a synchronous reset says, wait for the clock to actually capture a new value in the latch, and the new value that it captures in the latch or the flop will capture the reset value. So a synchronous reset can be done by taking reset bar, NANDing it with your data value, and sending that into the latch or flop, the rest of the element, as if it was the value you're capturing. And this NAND gate replaces the inverter that you normally would have had there to just have D go into an inverter. It now goes to a NOR gate or a NAND gate instead, that the other input to the NAND gate is a reset bar signal. So asynchronous reset, the way that you can do that in a latch, you do the same input NAND gate, but then in the feedback for the tri-state feedback for the state element, instead of having just an inverting tri-state feedback, you have a NAND gate tri-state feedback that also has the reset bar. So in this case, when the latch is open, the tri-state feedback is off, but we're sampling the value from the input, and you'll get the reset value going through. When the latch is closed, the tri-state feedback will be overridden by reset, and it will go through. So as soon as reset comes in, it will go through and overwrite the value of latch, no matter what the clock value is. Similar thing on the master-slave flop. You'll have the reset value going in, instead of at the very beginning of it, the reset value either goes into the master element, you replace an inverter with a NAND gate and reset bar, or you in the slave element have the tri-state feedback replaced by a tri-state NAND gate with reset bar. And again, no matter what the value of clock is, you're either sending through a reset value, whether clock is sampling or whether clock is trying to hold its state in the slave element. Similar to reset, there are occasions where you also want to set a flop or a latch to a value. So instead of having the output of the flop or latch coming out as 0, you want it to come out as 1. And sometimes you want to use both a set and a reset in the same flop. So below here is shown how you could implement a asynchronous set and reset function in a master-slave flip-flop. So it gets a little bit more complex, and you're just replacing different inverters with NAND gates or NOR gates being driven by either set or reset bars. So in each case, it causes a little bit of increase in the size of the master-slave flip-flop, but the overall structure is the same. So it's not an egregious amount of growth in order to get this functionality. In practice, there's usually relatively few master-slave flops that you might put set and reset on, but there are occasions where you need it in your circuits.